All right, so welcome back to OneClass. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So for the next hour, what we're going to do here is we are going to answer hopefully about 10 organic chemistry level questions. So these are basically questions you would typically see in a university and college level context, and I'll be trying to go over these questions for you, and I'll verify the solutions as we go on. Again, if you're tuning in for the first time here at OneClass, what our goal is that we are providing and curating these resources. So we're creating live streams and creating these videos for teachers such as myself to answer these questions so we can teach you the concepts behind these questions so that you're better prepared for tests and assessments as we go moving forward despite the COVID-19 situation. So that's kind of our goal here. That's our goal here at OneClass. Again, my name is Joey. I'm going to be your chemistry teacher for the session. I come from a background of having a bachelor's in science in terms of chemistry, and I'm also a high school teacher, so I'm a secondary school educator as well. So without further ado, let's get started on these problems that we have for today. All right, so our first question here is kind of a fill in the blank question. So this one here, these we have a bunch of key terms here. So we have alkyl boranes, oxidative, Suzuki, aeroboranes, metathesis, reductive, ligands, Heck, Simmons-Smith, Grubbs, and carbines. So we basically have these keywords. And we're kind of just matching these keywords. And this one, they actually already gave us the answer in this case. So we're not verifying the solution here. But I just want to go over and read to you like these some of these reactions here. So metathesis is reactions between two alkene molecules that result in the interchange of the carbons of their double bonds. So again, they're interchanging their double bonds between two alkene molecules. This is a metathesis kind of reaction here. Carbines here are neutral reactive intermediates that contain a divalent carbon surrounded by 6 electrons. The lone pair and two each form the R groups here. So that's carbene. That's what definition of a carbene is. A Heck reaction is palladium catalyzed coupling of a vinyl or aryl halide. It's good here. Ligands here are groups coordinated to a metal, which donates electron density. So you can think of ligands as in terms of a Grignard reagent, where you have magnesium has a metal here, and it's kind of bonded to the alkyl halide group, creating a negative charge that's kind of stabilized by the magnesium positive charge here. So that's kind of a ligand, example of a ligand. Reduction, as we know, is elimination of two groups that surround a metal. It creates C bond H or C bonds, carbon-carbon bonds here. That's good. Alkyl boranes have a boron atom attached to a benzene ring. So prepared by organolithium reagents by reaction with trimethyl borate. So again, if you have a boron atom attached to a benzene ring, it becomes an alkyl borane. Simmons-Smith is a reaction with alkenes and diiodomethane in the presence of copper activated zinc to form a cyclopropane. So you have alkene and you're forming a cyclopropane, and it's stereoselective as well for Simmons-Smith. An oxidative reaction is you're again adding a reagent to a metal, increases number of groups around the metal by 2. Finally, Suzuki is kind of like Heck, where it's palladium catalyzed as well, but then you're forming a new C double bond C bond using an organic halide with the organoborane. Whereas for the Heck one, it's a vinyl aryl halide with an alkene to form a new C bond C bond. So Suzuki and Heck are very similar in terms of palladium catalyzed, but one uses organic halide with an organoborane, whereas one uses a vinyl or aryl halide with an alkene. So I'm going to say the solution here is correct. Again, it's just a bunch of text here. It's just a kind of a fill in the blank kind of question here. Which is a great solution in this case. So number one was just basically just definitions here. Okay. That was number one. One was just a definition kind of question here. Okay, 2 here says which of the following complexes or complex ions has geometric cis or trans isomers. So we're looking at this one here. So we have the first one here is A here. A here is this is the complex here. So it's cobalt and then NH3 and then 2 and then Cl2 and then 2 minus. B here has a Cr group, NH3, bond 4, and then this is Cl2. This is plus. C here is another chromium group, NH3, 5, and then Cl, 2 plus, and D here is this is PT, NH3, 2Cl2, Cl2, oh whoops, 2, this is a 3 here, 2 Cl2, and it makes a square planar. So the first one here is a tetrahedral one. Again, if you have cobalt, it's bonded to 2 ammonium ions and 2 chlorines here with a charge of 2 minus. It says that here it's tetrahedral. So this one would not have an isomer here. This is a tetrahedral one. Will not have not have one here. This is a chromium as well. This here is a this one would give you a it's bonded to 6, has 6 bonds, right? So chromium here makes 6 bonds here, with 4 of them which are with ammonium and 2 of them with Cl2. Option B here is octahedral, right? Because if we were to draw this out in terms of Vesper theory, so we're looking at Vesper, and if you look here, we have Cr, and it's bonded to 4 different things. So it's bonded to 1, 2, 3, 4, and then 5, 6. So you have Cl, Cl, NH3, NH3, H3N, H3N here. So it's bonded to 6 different things here, right? This is a great example of octahedral group, right? So this here is octahedral for B here. C here is also an octahedral group. Again, it's just replacing one of these chlorines with a ammonium group, so it's also octahedral. So tetrahedral and octahedral shapes here. They have, this one is an octahedral for B, and C here is an octahedral for C here is an octahedral as well, and D here I would get a get something like a square planar, right? I have platinum in the middle, and then I would have basically this would be the NH3 group. This is the NH3 group as well. This is Cl group and Cl group here, and this one you could have a cis or trans isomer depending on the stereo isometry of the geometry of this one here, right? Depending on where it's bonded, maybe chlorine could stick out or NH3 can stick in, and it could have a cis or trans isomer. So option D here, I can prove to you that this one here has a isomer, because this here is a square planar and not a tetrahedral. If it was tetrahedral, then it would just be no matter how you rotate it, no matter how you rotate it, it's not a chiral center. So this one would not be it would not have a geometric isomer. So in terms of this one, A here is not correct, D here is correct, and we're looking at these two guys here. So we have option B and option C here, and both of these guys here have the number 1 here. So I have, again, 6 bonds here, and the chromium would have a positive charge here. And C here would have, option C here would have chromium having a 2+ charge. If it has a 2+ charge here, in this case, this would not be octahedral. This would be I believe it's a it's not a seesaw. Just give me a second. I have to, let me bring up Vesper theory, and let me just check that for you as well. There's a chart that says which kind of geometry it would be. So this one would have 6. So this one here would be a square pyramid. Sorry, this one here, this 2+ charge would give you a square pyramid. So square pyramids for C would have a square pyramid here type of shape, and this one would be octahedral in shape. So again, with octahedrals can also exist as cis and trans isomers, so it makes B the correct answer, and C here, square pyramids, cannot give cis and trans isomers. So in this case, B and D are the correct answers here, and they said here that's correct, right? B and D are the correct answer. D and B here. Octahedral can exist. Also, the platinum complex as a square planar can also exist as a cis or trans isomer here. Tetrahedral cannot. Also square pyramid. Ma5B here is square pyramid. Cannot give cis or trans isomers. So good. Solution and analysis. Good use of Vesper theory. So Vesper theory to solve the question. And what they could have put is they could have put actually a chart here for Vesper to say which geometry that they would have in 3D space, and then they would, in order for you to get that, then you could figure out if it is indeed, if it produced geometric or geometric isomers in space. So that's number 2. Let's look at number 3 here. It says predict the product for the following reaction sequence. So I have 3 of these guys here, right? So the first one here, so I have a carbonyl group here, and I'm reacting it with this group here. And I have H2SO4. And then the second one here is, I guess this is a 3-part question. And this is, again, I have a cyclohexane here, double bond here. I add H3O plus in heat. And then finally, if I scroll down here, I have here, this is a cyclohexane with cyclohexanal here. Not hexanal, but just an aldehyd here. With this is CH3COH. So this would be a bond OH here. Yes. Let me just double check here. Yes, this is correct. Okay, so take a moment to think about this question here. So I have, this is again, I'm predicting the product for the following sequence, right? So I have, again, I have a ketone here, and I'm reacting it with this cyclic kind of cyclic group, presence acid to form something. And then I have, this is a kind of an amine group here with a double bond here. I'm adding acid to form something as well. And then finally this aldehyde with this carboxylic acid. So let's look at this first one here. I'm going to see what they wrote here to see if they have the solution correct. So they wrote here that the first one here, they have the electrons from nitrogen here going towards this oxygen, and this would break the double bond to form this guy here. Okay, so and then they're doing a acid workup to produce this compound here. So let me just write this out and let me just verify it. So let's see. So they're saying the lone pair from nitrogen here is going to attack, and then this is partial negative, and this here is partial positive. It's going to attack this here, and it's going to kick out this oxygen. So when I do that, I would get something like this. I would get OH here, and then it would be attached to this N, and then you can draw out the O here. You get this group here. And then in the presence of acid, so H3O plus, this would be able to kind of, I have again partial negative charge here, and I have a partial positive here. So what it's going to do, it's going to add a negative here towards the OH2. So again, I would get something like OH2 here. So we get H2O. And so we have a positive charge here, and then I would have a nitrogen like so, and then I'm gonna maybe erase this and give it this is blue, I'll give it a positive charge here, and then let me erase this one to give it a positive charge here. And what it's going to do is, again, this nitrogen is going to collapse, this lone pair is going to attack, collapse on this double bond here. This is going to kick, OH2 is a great leaving group, so it's going to kick this out and then form the structure here. It's going to form something like this. It's going to form this double bond between N here. And then I have this. Is it like that? Yes, like that here. And this would have a positive charge here, right? And then finally, it's going to eliminate. Again, this H here is going to simply, again, you can think of it as an elimination reaction, or you can move the double bond to, basically it's going to resonance stabilize, right? And how it does that is this double bond is going to basically be brought down here. So this here is going to kind of bring this up So therefore, it's going to create a double bond within the cyclohexane group. So you get something like this. This would bond N here, and this is finally bond O here. So let me just erase this. Bond O, and this here would be our product here, and they got this one correct, and this one here is correct, right? So basically, what we did here was there was we did a nucleophilic kind of attack here on this double bond. It's going to form this kind of intermediate here. There should not be a partial negative here. Sorry. The acid workup makes the hydroxyl group a great leaving group for the nitrogen to kind of collapse on itself to form this double bond with the on the nitrogen, and then finally it's going to resonance stabilize to form something like this. So this here is a correct solution here. That's great. Number 1 is correct. So solution is correct. Let's look at number 2 here. 2 is kind of the same thing, right? So again, I have this kind of acid group here. What it's going to do, again, I have this, what they wrote here is that the nitrogen, the lone pairs of nitrogen are going to, again, attack here, or not attack, but it's going to shift and resonance stabilize here, and it's going to eliminate a hydrogen. So it's basically, this here is going to get kicked out, and basically it's doing the opposite of what we were doing here, right? So it's going to create a double bond with the nitrogen here. So this is going to go out. So instead of double bond being here, it's going to be back up top, like we said. So, like our thing before. This would now have a positive charge on nitrogen because I'm making 4 bonds. And then what it's going to do is I have my acid here. It's going to attack basically this. It's going to basically do a kind of like I would say maybe an SN2, or probably an SN1 reaction here actually. And basically it's going to kind of attack this double bond. Again, I have a negative charge here. It's basically going to make a hydroxyl group. So it's going to, the OH minus on the acid is going to kind of attack the double bond here. So it's going to break up the double bond. So you're going to form an OH here, and then form your nitrogen with your the little wings here. So this here, and with it, I still have a H here. So this is still partial, still positive here, and then what we can do now is that this here makes a very, very good leaving room. I can basically, again, do another acid workup and basically get rid of this, get rid of these guys here. So again, this lone pair from oxygen here can collapse here. This entire thing will get removed. So this here will form, again, I have, this is now my double bond O, and then it's going to bond H here. So this is a positive charge. Let me just erase this. This is a positive charge here, and then finally another acid workup would make it so that this the H here would just leave, right? If I were to H3O plus here, you can donate one of these. Take this hydrogen away, and we get a ketone here. So this is basically the exact opposite of what the first question here, which is totally fine, right? Again, what we're doing is we're looking at this guy here. Again, this negative charge is going to we're doing a resonance stabilization. So we're bringing the double bond back up here, making a great leaving group for the hydroxyl group to collapse itself on, and then we would form our double bond carbonyl group here. Finally, number 3 here, we have these are products here. So this guy was what we care about here. And we form it basically breaks these two guys up into a ketone, and then basically whatever the diamine group that we have here as well. And then finally we have this aldehyde group and a carboxylic acid group. Again, very, very easy solution here. What we're doing is, again, the negative charge on the oxygen here is going to come and attack this guy here. This one here is a partial. This is partial positive. This guy here was partial and negative, and what it's going to do, it's going to kick this carbonyl carbonyl group out here, and then let me just draw the arrow down so we have a bit more space here, and then we get something like this. we get kind of this intermediate here. So we have this here is bond O, this here would be now bond H, and this here would be now be bond O, bond O, and then bond O, bond, and then bond, basically something like that. This would give this guy here, this here would get a negative charge. Whoops, I want to do that in red. This here gives it a negative charge here. And what it's going to do is going to collapse on itself. It's going to collapse on itself and kick out this hydrogen here. So I would get a, it's basically just going to break these two guys into two parts, right? It's going to break this entire thing into a carboxylic acid plus a, your O minus here, right? So your O minus, like so. CH3, yep. So this here I would get something like this. And finally, what this student asked said, I don't know if I get a proton group here. Do I have acid? Oh, I do have heat. I do have. No, I don't have acid actually. Let me look back up here. No, I don't have acid here in this case. But assuming if I have like some sort of acidic, and it's done in a solvent, I would get. I can do acid work up here and get something like this. Yeah, like that. So these two would be my kind of products here. So this solution here is correct. I like how they showed the mechanisms and the arrows here. So this here is a great solution here. Great solution analysis. So basically, is again this question is asking resonance stabilization and basically nucleophilic attacks, making good leaving groups so that you form a different compound here. So the solution here is correct. Good. That was number 3, I believe. A very long question, number 3. This question 4 is kind of small, so I don't really know if I can see this. So this is I have a C triple bond N here plus MgBr. So this is a Grignard reaction. So I have a benzene group basically MgBr, and then basically over ether, and then H2O, what am I going to get? And then finally, if I add an acid workup, what am I going to get here? So basically, this reaction here is kind of a Grignard reaction, right? I have kind of a, this here makes it a positive carbon here. I have a positive carbon, basically on, like this carbon is very positive, because the bromine is basically makes it a positive carbon here. It's a nice Grignard reaction here, and I have again this double bond here is a very electron rich with this nitrogen here. So simply this is going to attack here, and then get rid of this bromine. So I would get something like this. Get C, and then I would have like triple bond and bond, and then a benzene group like so. So I get something like this, and then finally over acid and heat here, or is this? Oh, this is with the acid workup. Yeah, so that's fine. And then with I'm adding acid and water as well and heat. I would get this would be able to. I would basically kind of eliminate something, right? So let's see. If I have a benzene group here and I have a triple bond here, I don't know if elimination is going to happen here. So let me just see what they wrote here. So I have yes. So this here is correct here. I have this here is correct. This triple bond here is bonded to this benzene. The benzene here, and it's going to eliminate here. So I have actually a double bond. So this here, so yes, this here is actually a correct one here, because this I forgot that we also I had water here. So that's my sorry, an acid here. That's my fault. This here is H3O plus. H3O plus, and this guy here is I would have a double bond here, right? So I have the carbon like so. This guy would be a double bond instead, and I would basically link to this to the triple bond here. So this actually arrow is actually incorrect here. This arrow is not good. It's basically the triple bond that's coming to attack here as well. So this here becomes, it would make it a double bond, basically a double bond N here, and then this guy would be linked to my benzene group here. That's good. So I have that one here. So sorry about the I didn't clarify the arrows here. That's my fault here. And then finally I have H3O plus and H2O in heat. And what that's going to do is it's not going to affect basically the benzene group here, but it's going to change this double bond N here, right? Because I have, again, lone pairs on this side here. I have lone pairs here. So basically what's going to happen is that these lone pairs are going to take a hydrogen from the acid. So I'm going to get something like this. See, I have double bond N, bond H here. It's probably going to take actually two hydrogens. So this step is going to actually happen twice here to get NH2, and this here would become a positive charge, makes this nitrogen a positive charge here, and then I would have a benzene like so, and then basically this makes it a good leaving group for this OH to come and attack it, right? This OH here has a negative kind of dipole here. This one can go like so and actually kick this entire thing out, and we get basically this compound here, the bond OH, and then the benzene like so. And then finally what you can do with this one, it can actually oxidize and form the ketone here. So this guy can oxidize and form a ketone like so. So this here, again, this is just an oxidation reaction, right? Or you can say, I can basically say that it's actually just simply adding the double bond. So I don't think it's even adding the OH here. It's adding the double bond directly here to get this guy here. Because again, I do have an acid and I do have water to give me my protons here. So this here, solution here is correct. Great solution, but they didn't really provide an analysis, but no analysis provided. It's simply a Grignard reaction reaction to form basically the carbon bond. So actually to link benzene with the I guess this would be with the first group. So this would be a C double bond N. You can say it's with the alkyl group. I'll just say alkyl group, and then acid workup to I won't say acid workup actually. I'll say actually it's acid workup to get rid of to make nitrogen a good leaving group for water to attack to substitute it. So the solution here is correct. Great solution. Okay, so that was number 3. Let's look. Oh, that was number 4. Let's look at number 5 here. Number 5. So I have a cyclohexane in a chair conformation. Substitute 2 of the. I don't know what the question is asking here. Sorry. So it's saying, given a cyclohexane in a chair conformation, substitute 2 of the hydrogen labels with methyl and 1-methyl-propyl to construct the most stable conformation of cis 1-methyl-3 1-methyl-propyl cyclohexane. Use the number provided on the ring. So basically it's saying, where do we put these guys into this chair conformation to make it the most stable? So again, I have here, this is 1, 2, 3, 4, 5, 6. That's how they're choosing to label this chair conformation. And it's telling us, how do we label it to get the most stable in terms of the ring. So again, it's just another fill in the blank. So I'm just going to, just visualize it here. And as you can see, they put methyl here, and they put they put methyl into this group, and they put all the groups I care about are the methyl and the 1-methyl propyl, right? So they put the methyl here, the 1-methyl propyl here, and the methyl here. So this is good because what I don't want to do is I don't want to put the two big groups on the same side of each other. If they're on the same side, it's going to give me the highest energy level in terms of the conformation of the chair. So it's actually going to give me, if it's on the same side, it's going to be if it's basically both sticking up. So if I put kind of I'm 1-methyl propyl here and methyl here, it would both stick up and it would be on the same side. Although it is cis, in terms of the it would be basically in an equatorial, in an axial position. Sorry, if the same side, it's an axial position. So therefore, it would be the highest energy level, and in terms of it's actually the least stable for the conformation. But if you put in the equatorial position, like they did here, so I have 1-methyl here and 1-methyl propyl on this side, it would be the most stable conformation. So again, this is simply just the kind of question when we're talking about the chair conformation. We're talking about basically axial and equatorial positions. So again, axial, we have they're basically kind of the on the opposite side in terms of in trans, and equatorial would be kind of on the same side here for the cis as well. So that's kind of how we this concept of basically substituted cyclohexanes, and again, this here would have been a axial kind of conformation. This here is equatorial. Equatorial, I think of it as like inside the plane. Axial is always sticking up. You can also think of it as if you wrote, like if you kind of did a Newman projection, and if you were to see this in terms of if you were to draw the Newman projection, you would see that this one would be equatorial here. So you would see that both of these are in the most stable conformation here. So this is good solution and analysis. So the solution here is correct. I'm not gonna, oh, this is opposite. I have to stretch my head here. So this one is cyclohexane conformations. So that's good. Number 6 says, gotta twist my head a little bit, and let me write this down for you so you don't have to do that like I am doing right here. So let me write this down. If H3N bond CH, bond methane here, bond C, double bond O, bond NH here, bond CH2, and then COO minus. And then what it's saying, the question is asking, draw the resonance stable structure for the peptide bond below. Modify the molecule to show resonance form. You can modify by moving, adding, or deleting, or changing bonds or charges. You do not need to draw non-bonding charges here. I don't think they answer the question here. So I have basically this compound here, and it's asking us, can we move? We want to move we're moving our double bonds here or charges here to form a resonance structure, right? So what they did here was they did that the amine group here, so the N group here can move this way, so it bumps up this oxygen here. So this one would be considered a resonance structure, right? So I'll show you why. So this here is again a partial positive on this charge here because the oxygen is electronegative here. This nitrogen also has a lone pair, so basically it's going to come over here, and this is going to move up. So therefore, I'm forming something like so. I have again H3N. This is a positive charge on the nitrogen. CH3 bond C, and this would now bond. It would only be connected to one oxygen here, and the double bond is shifted to stabilize this nitrogen here. So this would be positive, CH2 COO minus, and this here would be a negative charge here. So again, this would be an example of a resonance stabilized compound. So this here is a great solution and analysis here. I'm just simply shifting this double bond from the O to the end, and I'm shifting the charges, right? That's what I'm doing here. So this one here is resonance stabilized. Solution here is correct. Okay. This here was the exact same question I did actually, so I think I picked a repeat one. picked a repeat one for this question here. So let me just verify this answer very quickly here. So again, it says here reaction on nitriles and Grignard reagent. That's good. And then basically they show you the mechanism. I'm not going to go through it through the Grignard reaction here, but you're basically going to get something like this, which is the final answer, and this here is correct here. So I'm just gonna like skip this question and say this solution here is correct because it's the exact repeat as the solution that we wrote before. So correct solution analysis. They actually gave us an even more in-depth mechanism in terms of the Grignard reaction first, and then finally the acid workup. So basically, again, making NH2 a great leaving group for this to collapse on itself to form the carbonyl group here. So correct solution analysis here. Solution is correct. So that was number 7. So I only have number 7 was just a repeat of question 4, I believe. So 7, that was a repeat. So totally fine. Let's look at question 8. It says draw the structure of the major organic compounds from below. So it says here, I have a benzene group here. And then I have some type of ketone here. It says excess Br and excess OH minus. So I have base, basically, excess Br2, excess OH minus. And this student wrote, the O minus here and not being able to complete the question. Okay, that's fine here. Let me erase this. So basically what's going to happen here is that, this is number 8 here, right? Again, basically in order for you to approach this question, what you do is you would draw the charges first, right? So again, I have a partial negative on this oxygen here, I have a partial positive on this carbon here, right? Partial positive on this carbon here. So what's going to happen is, and then I have excess OH minus, right? OH minus is a great nucleophile. It's going to come and attack this carbonyl group here. So basically, again, that's the first step here, right? So let me just show you what I mean by that. So again, this negative charge here is attracted to this positive charge. It's going to come and bump this up. So you're going to have benzene. Again, it's not going to affect my benzene group, but it's going to affect this here is OH. This here is now OH here, and this here is my kind of guy here. And let's see. So they wrote that it actually attacks the hydrogen here. So, and they're actually going to create a negative charge here. And then it's going to substitute on the oh, that's actually correct. Sorry. So this the reaction, the mechanism here is actually correct. And why is correct here? It's because I have the benzene group. So I totally ignored this benzene group. If this was a cyclohexane group, it would definitely do this mechanism here, but it's not, and it's actually stabilized here. So this would actually do an elimination. So sorry, I totally whiffed that. My fault here. It would do an elimination first. So this is going to be attracted to, this negative charge. This negative charge is going to be attracted to this hydrogen here, and this is going to get bumped up here. Or it's going to basically just create a negative charge first. So this O here, and then I have H here. So this here will become simply a negative charge here. And then what it's going to do, it's going to then grab a Br from this Br bond, right? So that's what this Br bond here, this is going to come and grab one of these guys, kick bromine out. So we get something like this. And this only happens with the benzyl group here. And then we get basically, and this is a alpha keto bromination for this the reaction. Firstly, so this here is my my reaction here. Again, bromine's added to the alpha carbon here, And then what's going to happen is, again, I can brominate this again much more times, because I have X as Br, X as OH right here. So I can do this basically reaction basically 2 more times to fully brominate this bond here, this carbon bond here. So it's Br bond to Br. And then what it can do now is that if I do this again, I have X as Br, right? So this is XS Br. So I basically do this alpha bromination, alpha keto bromination 2 more times to get this kind of compound here. And then what I'd get is, again, I have this OH minus now is going to attack this bond here. So this is what I did in the first step here. So the OH minus, so let me do that. The OH minus is actually attracted to, again, this partial negative, which is partial positive. It's going to be attracted to this guy here. It's going to bump this oxygen up and then create the thing I just erased here, right? So I would get something like this. I would get OH group here, and then get my carbon, and then, carbon here. This is bond Br, Br, and Br here. So it looks kind of weird. Again, this here has a negative charge here. And then basically, again, CBr3 is a great leaving group now. So it's going to come here and then basically kick the CBr3 out. And we get basically, I would get a carbonyl group now. So this would be a double bond O, bond, and then bond OH here. Bond OH here. And finally, and then this here, this entire thing gets basically kicked out, right? So this here would be CHBr3. This would be our chloroform here. So this here would get my products. You would actually get a carboxylic acid here, or do you get? Let me see if you get. Oh, you don't get acid workup actually. So this here would not. I would not have a hydrogen here. So this is simply the negative charge here. If I were to extend the problem, and if it were to have again an acid workup, if I have H3O plus, this would simply just grab a hydrogen and become a carboxylic acid here. But again, I don't have it in this question, so these two here would be my compounds. I have bromo form, which is CHBr3 because it grabbed the hydrogen from the OH group, and basically the H here is going to be grabbed onto with the bromo, the bromo form here as well. So I would get something like I would get this compound here, and then if I were to extend the problem and do acid workup, I would get a carboxylic acid. So this would be a benzoic acid here if I were to do acid workup. So great solution and analysis here. This was question. These are long questions. This is question 8. Question 8. Okay, let's look at question 9. So it says here, draw a structural formula for the intermediate in the following reaction. So I have some type of, sorry, my pentagon's really messed up here. Okay, that's the best I'm going to do with that one. Double bond here plus Br2 over CH2Cl. Cl2, right? So it's saying you don't have to consider stereochemistry. You do not have to explicitly draw H ions. Do not include counter ions here. So it says draw the structural formula for the intermediate in the following reaction here. So again, this pi bond here again is electrophilic, and what it's going to be attacked by the Br2 electrophile, right? So it forms something like this. So this negative charge here is going to come, it's going to come here, and then this here. Let me redraw Br2 actually. This here with something like that. This negative charge is going to grab onto that, kick one guy out, and then you would get basically something like I have to draw the intermediate. Sorry, so this reaction wouldn't happen first. So this one you would get something like this. You get, so this double bond would kind of be so attached to this carbon here. So you get something like this, Br and Br like that, and this would have a positive charge here. So this here is my intermediate for this problem here. This here is my intermediate, and then basically if I were to kick this bromine out, this one, that would basically add this one would the Br would come and react with this guy, and then we kick kind of the double bond out here. So you get something like this. So this here is our brominium ion here, intermediate here. So this solution here is correct. Solution here is correct. Solution is correct. They could have drawn the arrow as well. Again, it depends on I don't know what the extent of the question is. So solution is correct. Great analysis here. So this is simply just a bromination through adding basically a halogen towards a double bond here. Finally, number 10. Number 10 says indicate whether each structure is aromatic, non-aromatic, or anti-aromatic. Treat all structures as planar. So either aromatic, non-aromatic, or anti-aromatic. And then treat all structures as planar. So I'm just gonna, again, for the sake of time, I'm just gonna skip to these solutions here. And basically, again, it's saying it doesn't actually, this solution is actually not that great because it doesn't actually tell us the answers here. But it's saying A aromatic is 2 pi electrons, right? It goes 4n plus 2. This is the that's kind of the definition of an aromatic compound, right? So if I were to calculate based off the pi electrons for 4n plus 2, I would be able to figure out that this is aromatic. Non-aromatic compounds would be non-cyclic, right? So again, for example, E and B here are non-aromatic because they're non-cyclic here. And C here says, C here is, so this guy here is aromatic because 4n plus 2. Oh, A is, they answered the question, sorry. A is aromatic, 2 pi electrons, because I have the 2 pi electrons with the double bond here. So 4n plus 2, it matches this kind of formula here. B is non-aromatic, is non-cyclic good. C here is also aromatic, right? You have 6 pi electrons, again, 3 double bonds here. So this here is an aromatic compound. D here is anti-aromatic, right? Anti-aromatic is not 4n plus 2, but simply 4n, right? So if you have n, in this case, n equals 5, right? So if I count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 double bonds, which means I have 20 pi electrons. It does not fit the formula 4n plus 2. It fits the formula 4n, therefore anti-aromatic. And finally, E here is non-aromatic because it's non-cyclic. So the solution here is correct. Is correct. Great analysis, or good analysis, I'll say. It's basically just saying, again, I'll define it for you as well. So again, aromatic compounds, basically when we count the pi electrons, you need to have, if for it to be aromatic, it has to be 4n plus 2, right? So aromatic means that it has to follow this formula, 4n plus 2, and the anti-aromatic follows the formula of 4n, right? So it depends on the number in this case. It really depends on the number, and if it follows, if n is a whole number, then aromatic, it would be aromatic, and if it follows this formula here, it'd be aromatic, right? So again, for this one here, again, I only have 2 pi electrons here. So if I have only 2 pi electrons, so I can basically equate this to 2, right? So I would set this equation equal to 2, and you'll find that n equals 0 in this case. So this here would fit the it would fit the aromatic equation for the first one here, but it wouldn't fit the anti-aromatic equation, right? If I set this equal to 2, n would equal half, right? And I said n has to be an integer. Has to be a whole number here. So in this case, it would not be anti-aromatic, but aromatic instead. So this solution here is correct. Great analysis. And finally, the last question of the day, this question 11. I'm actually pretty surprised that I went through 11 questions here, but this is kind of great. A lot of these questions were going to fill in the blank, so I kind of skimmed over those questions as well. So it's saying, draw the structure of the organic product or products formed in the reaction. So let me just rewrite this. I have H2C, double bond CH, bond CH, double bond CH, bond CH, bond MgBr, right? So I have, again, a Grignard reagent here, and I'm adding D2O, right? So what's D2O? D2O is basically deuterium. D here is deuterium, and basically you can think of it as a hydrogen. It's basically an isotope of hydrogen. That's all it's doing here. So what it's going to do to this this compound here is again, I have a double bond in this place and this place here, and then I have a Grignard reagent, which means if I have a Grignard reagent here, I get a very, very positive charge on this carbon here is very, very partial positive here, and the magnesium just basically donating the electron density to this carbon here. So if I have a positive charge here, what is it going to do? You can think of it as, again, you can think of it as basically H2O, right? So you can think of, again, this this negative sign here is going to basically not the negative sign, but the lone pairs of oxygen are attracted to this partial positive here, and basically it can add and you can basically kick out this bromine, or there's this MGBr, and add this compound like so. So again, you get, this is the exact same thing as this first compound here. So again, let me draw it out for you as well. This negative charge. Sorry, this negative charge can come to this guy here and kick out this GBr. So this is the first product. CH1CH double bond CH. CH2, and then you basically get bond D here, bond the hydrogen here, because this entire thing is going to get kicked out. That's good. Or you can get, this is the first product, or basically what you could get is you could get a kind of a hydration reaction here, right? So if you look, let's see. So they moved the MGBr here. They moved the MGBr here. They moved it between the double bonds here. So let's see, the alkene chain. Yes, so alkene undergoes resonance and places deuterium at the center, right? So that would produce the second guy here. So let me draw that out for you. So we know that this here is the first. This here is the first reaction here. So this here is the first product. That's good. But what we can do with this guy here, as you can see, we have a double bond here and double bond here as well. And we have basically this can actually resonance stabilize to form something like this. It forms, basically, it puts the carbon right in the middle. So let me redraw this. So it's H2C double bond C bond, or is bond CH, sorry. Bond CH and then double bond CH here. Let me see if I got that right. Yeah, bond CH. Bond CH, bond MGBr. And actually, what it's going to do, it can resonance stabilize, right? So let me just draw the resonance stabilized structure here. Bond CH, bond C, bond CH2, and this would be MGBr. So basically, sorry, there was a double bond here as well. So basically, again, this double bond can it can hop. The electrons here can, again, move around to produce basically the most stabilized structure here would give the double bonds the furthest apart. So you get something like this, and then you could get but basically you could react this with D2O, right? And again, the negative, this here would have been, sorry, the blue one here is partial positive. This one would have been the negative ions here. Get this guy here, kick out this MGBr, and you would get this guy here as your second product, bond D here. And this would be the second product that places deuterium at the center here. So one, basically if it wasn't resonance stabilized, you would get the first product here, and second, you would get the second one here if it was resonance stabilized. So this solution here is correct. Great analysis. So that kind of finishes my video for today. Thank you so much for watching. We covered a lot in terms of 11 questions in the organic chemistry, in terms of the university level and the college level. If you like the videos, definitely subscribe to the OneClass channel, and you'll be able to check me and check some of the tutors out while we kind of go over this series of math, chemistry, economics, and other questions as well. So feel free to submit your questions there, and we'll try our best to answer you. Again, thank you so much for watching. I stream basically from Monday, Wednesdays, and Fridays in terms of math, and Tuesdays and Thursdays in terms of chemistry. So thank you so much for tuning in. As always, again, stay safe, stay healthy, and have a great day. Don't stop learning. Take care.